Hello.
Yes, sir, you
Hello.
are audible.
Yeah, I'm audible, right? Okay. So, um, yeah. Any questions about whatever has been going on?
Sir, I had mailed you some
Yes, you have
queries
mailed me some
regarding the
questions. I just saw
assignment.
it actually. I was not available in the weekend, so I will reply back to your mail right after the class.
Okay, sir.
Yeah, it's about the assignments, right? Some doubts
Yes,
about the
yes.
assignment. Yeah,
3 questions.
3 questions. Yeah, I will do that. Yeah. Any other questions about what all things were going on? Because as I told you, from today we will be changing gears significantly. Okay, not gears, in fact, changing direction to some level. So, so till now, what we had done is what can be called as a standard introduction to algorithms class, in which we picked up some problems, some toy problems in some sense, maybe you can say, but they're not actually toy problems, they're important problems which are kind of small building blocks to other algorithms and all. And we looked at this set of problems, and we use those problems to study uh, various approaches one can take to solve a problem, right? And now all the problems that we have seen so far are what can be called as polytime algorithms. So algorithms in which we have a very nice efficient algorithm, where efficient basically means it is at worst quadratic or cubic in the input size. Most of them can be done even lower, even linear sometimes, right? But actually, in real life, the problems that we normally face, they are not as simple. Okay, and not as simple. I don't mean this simple meaning that they're tough to work or to come up with an algorithm. No, they are problems for which we don't even expect to have a polytime algorithm. Now, how do you handle this kind of problems? What does mean by non-polytime algorithm, kind of stuff like that? I mean, you have been kind of almost to some level been what to say? Yeah, hello. Yeah, your mind has been kind of told to that whenever we write about efficient algorithms, you should talk about an algorithm whose runtime is n square or n log n something. But that is not at all correct. Okay. And the other concept that we are going to talk about is something that we have done a little bit here earlier, is that there are lots and lots of problems in the world, right? You go and start a job somewhere in the industry or something, or you do a research and all, whatever it is, you will find a problem that you have to solve. Now, will that problem be a very uniquely different problem? Do I have to completely start finding a solution to that problem from scratch all the time? Or is there some standard way of approaching these problems? Okay. Now, it is true that sometimes starting from scratch is done, and that's a part job of the researchers and all. But that's not very common. Most of the time, we don't solve the problem from scratch. Instead, what we do is what we reduce problems. So there are some kind of massive hammers that are there, that we kind of try to convert the problem into some form so that we can use those hammers to beat it down. Okay. Now this was something yeah, so something similar to that you have done earlier, long time ago in your high school when you used calculus. Calculus was a massive hammer for solving a lot of problems. Here also we will talk about these big hammers. So let me start with some. Let me share my screen. And yeah, so let me start with problems. So till now, we have seen problems of two kinds. Okay, I kind of told you guys, I think also, that there are two kind of algorithms, problems. One of them is what is known as the, we will call it as optimization algorithm. Okay, optimization problems. And the other one is called the decision problems. So optimization problems are problems in which your job is to find a solution. I mean, find a solution that optimizes something like find the minimum path between a minimum length path between 2 points, or find the smallest vertex cover in a graph, or find check whether the find the maximum number of objects you can pick in a knapsack, and so on and so forth, right? And decision problems are basically saying that whether a particular instance is within so the decision problems are something for which there's only yes and no instance. So let me give you an example here. So like here, as I told you, what is the shortest path from U to V? Now, when I say what is the shortest path, it's an optimization problem. It's saying that, okay, find the path between U to V that minimizes the distance, right? A decision version of this problem is there a path from U to V of length less than or equal to K? So this is an yes no instance. This is not an yes no instance. This is a instance that is outputting something that can take, if you are talking about outputting a length, you're outputting a number, an integer, a number, basically any number. And this is a yes no instance. Now we will be talking about these two concepts in some sense interchangeably, okay, in the next 3-4 classes. Why? Firstly, because if you can solve the optimization problem, can you solve this decision problem? What do you say? I can see a lot of new faces. Wow, and so
Of course, sir.
Yes, sir.
sorry, yeah,
Yeah, certainly.
We can,
right? Okay, how?
yes, sir. Because we know the shortest path. So if k is less than the shortest path, length of the shortest path, then the answer will
I
be
can
no.
do it. Right.
And
Very
if it
good.
is greater than the shortest path, then
Exactly.
answer
So
will be
optimization
yes.
question can solve the decision question. What about the opposite direction? Can a decision question be used to solve the optimization question?
So just by knowing it's an existential answer, knowing the existence of something doesn't necessarily implies they will know it exactly.
No,
what it
even
is.
if you know the existence, even will you know the what is the length of the shortest path?
No, they will know it.
If we
Can we ask?
Yeah.
So can we ask repeated times? Like
Can ask repeated time. How many times?
then that depends upon the number of edges there is, but we can repeatedly ask whether for maximum number of edges we can ask, then we can reduce, then we can get to know the shortest path, right?
Yes. How many? Reduce how many times?
Till the number of edges actually.
So how much? How much? Give me number of edges.
Yes.
Okay. Can you do better?
from 1 to k, we can keep checking, and that will be bounded by k then.
Okay.
No, but if
Yeah.
the first k you start with, if the answer is no, you'll have to go up to something exponential, right? Keep on going.
Exponential.
Like
What do you mean exponential?
the total number of edges possible.
Total number of places possible is how much? Say n, right? M.
Oh no, n square, n square. N into
Okay,
minus
n
one.
square. Yeah. So do you have to go n square?
We can
Hey,
perform a binary search type of thing.
You can perform a binary search kind of thing. Why did you learn binary search for this kind of stuff only?
No. Sorry. It won't give you the greater or less than thing.
Of
No,
course,
no.
it will give you. What do you mean? I will ask, is there a shortest path or is there a path between u to v less than n square by 2? If it says yes, there is, I will go down to n square by 4. If it says yes, I'll go down to n square by 8. And then if it says no at some point of time, I know that it has passed. So I will ask questions. I will basically, I know that the maximum that it can take is n, minimum is 0 or m, whatever you want to call it, n, m, doesn't matter. And I can, and somewhere here, right, is the shortest path that I'm looking at. And I can choose k anywhere. So I can first choose a k over half, then choose a k here. If I say no, I will move in this right hand side. If it say yes, I will move in the left hand side.
I have a question.
Yeah.
In the optimization problem, are you just outputting the length of the shortest path?
Okay, let's start with the length. Okay, even that
Okay,
also
okay.
can be done. Think about it. Okay, you will very soon see that that also can be done. You can actually output the exact value.
And you can do that in decision as a decision problem as well.
First of all, find the length. You can do it in decision problem.
Yes.
Okay,
I see that. Yes.
finding the shortest length of the shortest path. Okay, and then from length to actual finding it out, think about it. You can do it actually in again order n times. Okay. So more importantly, given this decision function algorithm, using just a log n overhead, you can solve the optimization problems of this thing also. Okay, just log in. Yeah. And now if you are worried about whether the existence of something and actually finding it, you can do it with another linear time blow up. So if this thing can be done in order t, this thing can certainly be done in order t times n, but n is the size of the algorithm, the size of the graph. Okay, basically instead of talking about find the shortest path between u to v, you find the shortest path between u to w, where w is any of the vertices that come from from which there is a edge to w v, right, and find the shortest of them. So this is something crucial to understand, and in the next few classes, is there any doubts over here? Hello, there are people who are asking questions. Is it clear?
No, sir. Yes, sir. It is clear.
Okay. So I will be talking about this optimization problem sometimes in the next few classes, and sometimes I'll be talking about the decision problem. Okay. And more importantly, yes, it is true that if you will say that, oh, if it is can be done in t, then this can be done in t times n. How is it same? Yes, they are not same. You're right. But first of all, exact knowing this one, it can be done in t times log n also. So there's not that much of a difference. But more importantly, if this number t is quite a lot more, it's more than polynomial, then you know that this n factor is not something that is going to cause you a lot of problems. I mean, in terms of complexity of something, we say that this problem and this problem has similar complexity. Okay. Because if t is something like up to polynomials, it is same. So let me start with, first of all, trying to understand this concept by using some examples. So first of all, we are talking about optimization problem in today's class. So the main job is to maximize or minimize something as long as the solutions satisfy certain kind of equations, certain kind of conditions. Okay. Good. Sorry. Yeah, so there are some examples that we have already seen. The shortest path between S and T, the knapsack problem, find the best regression, the best SVM optimization, the best k-means clustering. All of them are typical optimization problems when you optimize something. So here is an example. Now this is of course a toy example to some level, but is not. I'm going to give you 4 problems, one after another. And I want you guys to read them very carefully and see how you will approach each of the 4 problems. Okay, here is the first one. Okay. Yes. So company basically has to ship as much goods as possible, but it has only 3 wagons that they have, and it has 4 kind of cargos. Okay, and each wagon and each cargo has different kind of restrictions, right? So each cargo has how much of tons are available. Okay, this much ton is available. There's a volume per ton and there's a profit per ton. Not all cargos have same kind of an idea, right? It's a shipping company. And in terms of the wagons, each wagon has a capacity of both on the ton of the weight it can carry and on the amount of space capacity it has. Okay, so for example, if the wagon is taking C1 only, it can take only 10 tons of C1, but in that case it will require 4,000 tons, 4,000 unit of volume, which is this much. Good, it will be less than 5,000. So the profit that it will get is just 20,000. It can also take, say, maybe 5 tons of C1 and 6 tons of C2. And then you have to calculate whether the volumes are more or less make sense or not. And you have to see which is the maximum, the profit will be accordingly taken off. So the 5 times 2,000 plus 6,000, 2,500. So think about yourself, put yourself in the shoes of a person in a company who has been asked to solve this problem. How will you fix this problem? How will you solve this problem? Is this problem clear?
Sir, just one question. In this particular case of values, the space capacity constraints of the wagons are being like irrelevant to the
For this
constraints.
particular instance, yeah. So maybe you should not look at it this particular instance kind of stuff. Think of them as general.
Yes, yes.
Okay, so so this instances is possibly, I mean, that you cannot optimize. I mean, in terms of
Like we can just optimize based on weight capacity. in this
possibly you
instance.
can just optimize based on weight capacity for this instance of this problem, right? But I mean, I'm not sure that also you can. Yeah, possibly you can do that.
Yes, the maximum volume per ton is 500. and
Correct, that's true.
The lowest for wagon 2 is 500 as well.
Yes, yes. Yeah. For that particular instance, that's a different thing. But in general, what will you do? How will you do it? Okay. What about others? Did you guys manage to think a little bit on this? Sorry, I cannot hear you, Thomas. Is there some disturbance from your end? Hello? Hello. Okay, maybe should I ask people one by one? Devdatta Kanungo, are you there?
Yes, sir.
Is this problem clear?
Yes, sir.
Sure.
Yeah.
Okay, well, I will ask you to solve this problem. So how would you? Okay, so let me go over it. Let me see what I think. I have all the 4 problems one by one written there, and then we can decide on how to go about it. Okay, so let me go to the next problem. Okay, the next problem is what is known as again, this is something that is used a lot. It's called a bang for buck advertisement. So basically, your company has given you 6 crore rupees to spend on advertisement, and your job is to reach as many people as you can. Now you can spend it on advertisement during Cricket World Cup, and it will cost you quite a lot, and you have an expected amount of people you can reach. But at the same time, you have to ensure to get full of such this feat, you have to employ or put so many of your human resources into it, right? So this says that okay, 5 people will be required for that time, and you only have 10 people. So if you want to plan to work on put advertisements on Cricket World Cup, this is what you do. If you want to put it during the IPL, then you can, cost will be 5.2 crores. You will be reaching out to more people, but also you will have a more number of people that you want to employ, you have to employ. And these are like, you cannot, the issue. So the previous problem, the one useful thing was that there is no constraint on the I could take X amount in C1 and Y amount in C2. Yeah, who cared? Here that is not allowed, right? I cannot say that okay, I will only sponsor for half of the Cricket World Cup. That is not how deals are done. Cricket World Cup says that okay, you want to, oh sorry, yeah, just give me just 2 minutes. Hello. Hello.
Yes, sir. You're audible.
Yeah, you're audible. Yeah. Just yeah. So here, the way in which it works is that you cannot take half of the Cricket World Cup and half of IPL. No, such things are not allowed. Either you take or decide to put it in World Cup. In that case, you need to invest 3.45 crore and you need to get 5 people into it, or you can go for IPL, and similarly for other things, right? So they can be radio ads in FM, they can TV ads for non-peak hours, TV ads in peak hours. There are various kind of constraints that are there. So what is the best way of spending your money? Okay. So I hope you guys are kind of taking a note of this thing and remembering some of it, right? Yeah.
I understand this problem, but the first one I don't understand. Can you explain it once again?
Which problem? The previous problem you could not understand.
Yes, sir. Wagon and cargo.
Okay. So see here, yeah, hello.
So before you proceed, can you just mail the slides to our Google Groups?
Right now, okay,
Yes,
let's
then we can go through the.
to our
I
Google
can
group. Mm,
like we have Google Groups for both MTechCS and MTechCRS. I'm dropping them in the chat. So I think that will be okay.
just 1 second. Let me. Okay, let me stop share for a short time. Let me do one thing. Just 1 second. I think it'll be much easier for me to upload the slides in the web page. Just give me just 1 second. Today's second, right?
Yes, sir.
Yeah, in the web page, it is now published. Can you check?
There is lecture 20.
Yeah.
I can only see up to lecture 19.
No, there is lecture 20. Just like as the refresh
Yes,
on.
it is available now.
Yes, it is.
Okay. Where did I share screen? Yeah. So let me continue with the share screen thing. Yeah. So think of this way in this, so this problem in this way. So you are in you're a shipping company, okay? In which case you have been given that, okay, you can ship either some coal, which is you have 18 tons of that coal, but for each ton of coal you will need 400 units, 400 meters square, not meter square, yeah, 400 something, 400 meters square volume is required. And the amount of profit, you have been told that, okay, for every ton of shipping you will be getting $2,000 or something. Now you also have the iron ore, which you have less in quantity, the 10 unit, and the volume that will be required for each 10 unit is 300, each of those 10 units, and you will earn a little bit more for that, and so on. Okay, so this is the given set of cargo that you have. Now you as a shipping company currently controls 3 ships, the W1, W2, W3, or 3 wagons in terms of the railway wagons, whatever. Now, each wagon has a limitation of how much it can carry. The limitation is based on what? Limitation is based on its capacity and its volumes that it has. So it is allowed to carry 10 tons of objects. So all total weight of the object that it is carrying is 10 tons, and it is at most allowed to carry about 5,000 meters square of volume of weight of objects. So you can choose that, okay, I will take, say, 5 tons of cargo 1 and 5 tons and cargo 2. Okay. Now that would be saying that, okay, if you take 5 tons of cargo 1 and 5 tons of cargo 2, the total weight in volume, so 5 plus 5 is 10, that is less than 10. Okay, I can put it in cargo wagon 1. The volume that I will take is 5 into 400 plus 5 into 300, which is 3,500, which is also less than the wagon capacity. So I can take 5 tons of cargo 1 and 5 tons of cargo 2, and the profit I will get from wagon 1 is 5 into 2000 plus 5 into 2500. So that is, I can say, okay, now good, you have gone, take it home. But then I have wagon 2. I can say that, okay, since I have already used 5 tons of cargo 2, I am only left with 5 tons of cargo 2. Now this 5 tons of cargo 2, maybe I can shift it to through W2. Okay, in W2, let me say send 5 tons of W2, and I still will have 3 tons left. So maybe 3 tons of W of C3. So 3 plus 5 is 8. Okay, that is less than the wagon 2. In terms of capacity, it will be 5 into 3000 plus 3 into 200, which will be around 2100. Oh, that's less than 4000. So wagon 2 can be shipped accordingly, and the profit I will get is now from wagon 2 is 5 into 2500 and 3 into 5000. Now what about wagon 4? Wagon 3 has 12 tons. Now I can, okay, since wagon 3 has 12 tons, I can send all the 12 tons I can use from cargo 4, and this 12 tons will cost me, or will take 500, which is like 6,000 space, which is less than this. Okay, and the volume that I get is 12 into 3,500. So this is the profit that I can get. This is one particular way in which I can ship some of the objects. But now, is this the best? Would I have done something else that would have maximized my profit? Our job is finally to maximize profit under certain restrictions, right? What are the restrictions? That at any point of time in the wagons, I cannot take more than its capacity. Any times in its wagon, I cannot take more than its space capacity. And for none of the cargoes, I can take more than whatever amount is available. Under that constraints, I want to maximize profit. So there are 3 constraints, and I have one maximization that I need to do. So is this problem clear?
Yes, sir, it's clear.
It's clear now, right? Okay. Yeah. So how do you solve this problem? That's the main question. Okay. So similarly, there was this one, problem 2. Let me give me another problem, problem 3. Now, this is something that is very, very common in your life in some sense, right? So there are some N MTech students, and there are M faculty. Now, each student will submit a list of faculty names with whom he or she is interested in doing thesis. And each faculty will say that, okay, submit a list of students whom he or she will be happy to supervise. Okay. Now, also each faculty says that submits a number denoting the maximum number of students that he or she is willing to supervise this year. So something like I can say that, say I'll be happy to maybe take this or this 5 students as my, or any of these 5 students as my PhD as my master student, but I cannot take more than 2 students. So these are the 5 students that I can take, but at most 2 of them.
A question, like in the stable matching problem, are you giving a preference list?
No,
or
there's
just
no
saying that
preference
any 5?
whatsoever. There's no preference.
Any 5.
I'm just saying that is there a solution? There's no preference whatsoever. Is it possible to find a solution? Is there a solution? Okay. Can you design something that will everybody is constantly satisfied? Fine.
Yes, I understand.
Yes.
So this is the third question. The fourth question is a completely different area from which it is coming. So there are, say, n important locations in a city. Okay, the telephone company has now decided to upgrade it to 4G locations. So the idea is that in this n places, so they want to upgrade each of the locations, if they are towers and whatever stuff, install some special stuff, so that these n locations is covered by 4G network, 5G network. So the idea is that, okay, if I can put a tower within a 1 kilometer of another of some place, then the 5G connection will be pretty well maintained. Now, of course, the company wants to minimize the cost of upgrading these towers. Right? They want to spend less so that the maximum amount of important places are covered. How do you solve it? What is the minimum amount of price that the company has to spend? And this is something you cannot even imagine. All these questions are how important is it? I mean, this telephone tower problem is something that massively important. As you can see, that continuously checks about how to upgrade facilities, that comes up all over the place. This problem has other important things. I mean, namely, this kind of typical teachers allocation in the colleges, various matching problems this can be solved through this particular problem. This bang for buck in advertisement. This problem, although this slide was written some 5 years ago, and that's why it is this one. But you will be surprised that this is exactly the problem that is being solved right now. Okay, so that the vaccination campaigns can reach the maximum number of people. The COVID vaccination things and all. So these are all very, very, I mean, in other forms, these are very important questions that comes up again and again and again. Now the question to you guys is that how will you solve them? Okay. Now I would have loved to given you a lot of time to go and think about it and all, but I don't think I have that much time. So I will maybe jump ahead and just talk about just the first problem. Oh, there's some other problem. Okay, let me not go into this scheduling of meetings. Let's not go into this particular problem right now. You can go and look at the slides and understand. So, as I told you, the meaning of these problems can be modeled as a third problem, a third, much more general problem. So I want to know how many of you have actually heard of this concept of linear programming, or seen or worked with it in some sense. Linear programming. Can you raise your hands? Anybody has worked with it? Okay, I can hear 1 person, 2, 3, 4. Okay, 5, 6. Oh, very good. 7. I can say a lot of people. So to this set of 6 or 7 people, can I assume that you guys have managed to solve the first problem?
No, sir, I cannot, because I have to brush up a little first.
You brush up a little,
This is
okay.
my graduation.
Okay. So basically, linear programming is a very generic problem. Okay, it's a very abstract problem to some level. It says that your goal is to maximize a linear equation of this form, any form, linear equation. You know what a linear equation, right? Right. So maximize 3x plus 4y minus 10z. But x, y, z is the variables under some set of constraints. What are the constraints? Any constraints. They all have to be linear. That's the only property. That 5x plus 8y is less than 15. I mean, it doesn't matter what I'm writing it. Okay, they're all linear equations or inequalities you can think of. And this is called linear programming. Okay. Now, we will not be going deep into linear programming because this is not a course on linear programming. So I will not be training you about how to solve linear programming as such. I will only talk about some very high level stuffs on that or tell you some pointers only. But is this problem, is this definition of linear programming clear? What is linear programming? Okay.
Yes, sir, it is.
It's clear.
It is correct. Okay, Shubinoy Hatai,
Yes, sir.
is it clear what is linear programming?
Yes, sir.
Okay. Venkatesh,
Yes, sir.
clear, right? Any questions? Okay. Kuntal Pramanik?
Correct.
Kuntal Pramanik,
Yes, sir.
it's clear.
Yes, sir. Yes.
Okay. So if it is so clear, then can you write down? Oh, so this is the important thing that here I have not written this thing, that I'm assuming that x, y, z are real numbers. What something weird happened? Yeah, x, y, z are real numbers. Okay, and this is the standard linear programming. It's called linear programming, LP. I've only, this is an example. I'm giving you a definition using example, which is not a very great way of doing it. But I hope that you guys understand it from the examples better.
Sir,
Yeah.
so the definition essentially boils down to the fact that the optimization problem and the constraints both would have to be linear equations.
Exactly. That's it.
That is all.
That is it. Okay. Both have two linear equations. Okay. And the variables are real numbers.
Yeah. Okay.
Okay. So that's it. I mean, I can give you a mathematical formulation. This is the dot product of a vector with some with a random vector, random variable vector, and this is a matrix inequality. But don't even have to go into all of that. Okay. So all the thing that you are going to maximize, or it can be minimization also, to maximize or minimize under a constraints which are all linear, and the x, y, z are real numbers. Now this is a very powerful tool. This can be solved very quickly in polynomial time. In fact, there are some very nice packages also to solve LP. So if you have ever worked on this programming called R, there's an LP solve is a kind of software that does it. So the important thing is that, okay, I don't need to go into all of this. Okay. So this is a very well studied problems, and this is the important thing. When the variables are allowed to take real values, which is the normal LP, this can be solved very quickly in polynomial time. There's an outstanding set of algorithms that solves it in polynomial time. And this is some important things. Okay. The trick about solving many of the problems is modeling the problem in LP. So this is a big hammer in some sense. So can you now write down this problem 1 as an LP constraint. Let me see. Let me give you a couple of minutes to think about it. I have in fact reduced it. I have made this LP problem a smaller problem. Earlier I had 4 cargos and 3 wagons. Now I've made 2 wagons and 3 cargos, just to have the instance smaller. Just think about it a little bit and try to solve. Yeah, any ideas?
So we can frame the optimization problem as allocating, suppose the K11 would indicate that W1 contains C1 of that amount,
Very
K12
good.
W1 contains C2 these amounts,
Right.
and then we
right.
optimize on K11 P1, K12 P2.
Right.
K1,
So here is it, right?
and the constraints.
So I have not written it W1 and all. I have written it in X1, XY1, X2, Y2, X3, Y3. X1 is the amount of C1 being loaded in W1. Y1 is the amount of C1 loaded in W2. X2 is the amount of C2 loaded in W1. Y2 is the amount of C2 loaded in W2, and X3 and Y3. Now, right, so in some sense, this is for each cargo there is X1 and Y1, and for each wagon there is X1, X2, X3, and Y1, Y2, Y3. And once you have that, what all constraints can you say? First of all, what is it? What is the profit for us? Profit is nothing but maximize 2000 into the amount of things that are going. So it is X1 plus X2. 2500 into X2 plus X3 Y2, and 5000 into X3 plus Y3. And what are the constraints? First constraint is that the amount of cargoes available is enough. So X1 plus Y1 is less than 18. X2 plus Y2 is less than 10. X3 plus Y3 is less than 5. Right? This is one constraint. What is the other constraint? Somebody help me out. Actually, I think I want somebody. Kuntal Pramanik. Hello. Yeah, can you help me with one more constraint?
The non-negativity.
Huh?
The non-negativity.
Oh no, other than the non-negativity, some other constraint.
Sir, X represents the total cargo going into the first wagon. So
Right.
X1 plus X2 plus X3 cannot exceed 10.
Right. X1 plus X2 plus X3 cannot exceed 10. So non-negativity is a constraint, but yeah, I understand that. So all the X1, X2, X3 has to be bigger than 0. And this is the X1 plus X2 plus X3 has to be less than 10, and X1 plus Y1 plus Y3 is less than 8. And who is going to say the last one?
So 400 X1 plus 300 X2 plus
Right.
200 X3 less than 5,000.
Yes. So these two volume constraints, right?
Yeah.
Because it's in cargo 1, it is 4,400 times X1 plus 300 times X2 plus 2,200 times X3 is less than 4,000. And the non-negativity constraint. And that's all. You solve it. So this problem looks so daunting to start with, right? But if you have been given this particular LP formulation, then this can be done quickly, right? Wonderful. Any
One
questions, any
thing-
doubts?
Yeah, the whole thing about polynomial time solvability is under the massive assumption that x1, x2, x3, x5, and all these variables are real numbers, right?
They're all real numbers, yes. Very much true. They're all real numbers.
Otherwise, it's not true.
Otherwise, it's not necessarily true. That is true. Okay, so this is the transportation constraint, and the real number, and it can be solved in LP solver. Let me go to the next problem. What about the problem 2? Can you write in forms of an LP? Yes, I can hear 2 people who have raised their hand. Yeah, Devarshi?
So we can allocate in some sense some indicated random variables whether each of the advertisements are chosen or not,
Yes.
and that multiplied by the expected reach would give us the optimization function, and based on that we can implement the
Right. So we can have this we can have now the 0, 1 variables, x1, x2, x3, x4, x5, depending on which one of them I am choosing. So 0 means I'm not choosing that one, x0 means 1 means I'm choosing that one. That means if I can have this constraints over here, I can now define this optimization function, whatever. I can define the optimization function as maximize the amount of people that can be reached, which is just nothing but this thing. Under the various constraints, what are the constraints? Number 1 constraint is the cost must be less than 6, and the number of people must be less than 10, and there will be of course a x1 to x1 is a positivity constraint is there. The issue is that this is not an LP. It is because of this constraint. This is not an LP because the x1 to x6 are not allowed to take arbitrary real numbers. It is only allowed to take numbers 0 and 1. Okay. And surprisingly, as soon as you ensure or you are forcing me to put the variables as integers, this problem becomes a hard problem. This doesn't have a quick time solution. It doesn't have a polytime solution. Okay. Now, okay, is that done? Is that something? So there are some fixes that you can do for this problem. Okay, let me go a little bit out of my way and just talk about it. So one is called this relaxation of the constraints. Like instead of having this values as x1 to xr to be 0 and 1, what happens if I just say that I am just going to insist that x1 to x6 are between 0 and 1? They're real numbers. Now, of course, that doesn't make any sense because what is meaning of you pick say Cricket World Cup with 0.25 and IPL with 0.85? Doesn't make any sense. Of course, it doesn't make any sense. But sometimes, for the sake of computation, we relax this problem. And now we can solve it by LP. Say I get this problem. And then what one can do is that using this P1 to Pn as solutions, you can come up with a proper solution. For example, you can think of them as probabilities and so on and so forth. Okay. But the most important fact is that we could not, maybe I should go here and say it, that yeah, so we had picked up this LP. This LP, this was has a polytime solution. Okay, this is good, but the one that I just now wrote is called ILP, meaning integer linear program. Okay, now what is an integer linear program? It is exactly same as LP, where the variables have to be integers. Variables, you can put a constraint that variables have to take integer solutions. So like x1 to xn has to take an integer between 0 and 1. So either 0 or 1. These problems is hard. Okay, now let me define P, the class P. How many of you have seen the class P? How many of you have done the TOC course? The automata theory course? Or how many of you have not done TOC course? Let me ask you guys.
We are some of us are doing the automata course in this
Right now.
semester because it's in second semester for MTech series.
Right. And what is going on now? Has Turing machines come in there?
No. We are just doing push down automata right now.
You are still doing push down automata. Okay, so let me just define P then. P, this is the class of or set of all problems for which there is a polytime algorithm. Okay, so this is a very vague definition. And possibly you should live with this definition only. Because to get the formal definition, I have to talk about Turing machines, I have to define about various things. But you know, people who have done automata, you know that there is a concept of languages, right? And so I can talk about what is the language L. And you have talked about whether the language is in a regular language or language is in CFL and all. Similarly, we can define whether L is in P if and only if for all x in sigma star, okay. Oh, sorry, I should not use this one. If and only if there exists an algorithm A, okay, such that for all x in sigma star, A of x comma L equals to 1 if x is in L, 0 if x not in L, and runs in time polynomial in size of x steps, polynomial in x. Okay, now what is polynomial in x? Of course, when I am defining this thing, I have to say that there is the algorithm A and a polynomial P such that, maybe I should write it here, so that A of say takes less than or equal to P times the size of x steps. I am still not defined you what is an algorithm, and this is a concept I cannot define you without a Turing machine. But you have some sense of what is algorithm, right?
Sir, just clarification. When you say algorithm, that's just a deterministic Turing machine, right?
Yes, that's a
Or is it-
deterministic Turing machine.
Oh, okay.
That's it. Okay, so this is a formal definition of what what the class P is. Okay, informal definition is the set of all languages that are for the problem that can be solved in polynomial time. So, but since you are talking about this thing, so this is sometimes called set of all decision problems. Okay, the set of all decision problems for which there is a polynomial time algorithm. This is called P. Fine.
Yes, sir.
Okay. How much time do I have? Okay, I don't want to go too far today. So what we can say is that the LP is nothing, not a language or anything. It's a linear programming. The problem linear programming is in P. Okay. Good. What all things else we are having in P? So whenever I'm talking about P, I might be a bit shaky here because I'm going to talk about optimization problems. But whenever I'm saying this statement, you should think of it as not an optimization problem, but as a decision problem, formal definition of it. Meaning whether that optimization, there exists an optimization value which is less than K or more than K. That is the decision version of the problem. Okay. So whenever I'm saying that LP is in P, I mean the decision version of LP is in P.
Haven't you shown that if decision version of LP is in P, then the optimization can only...
Correct. I'm just saying is that you're completely correct, but this definition is only for formal definition is only for decision version. So don't be say like, oh, you have given me a definition of P for decision version, and now you're writing a statement for optimization. Okay. So this statement is for the decision version. Okay. Although the class P is defined for the decision version only. Okay. Now you have also seen the shortest path is in P. The minimum spanning tree is in P. And a lot of these things are in P, right? Okay. Now, you know what? I suggest that, okay, so then there is this class which is called non-deterministic polytime. Let me ask you guys a something that will help me a lot. You guys is there anybody who has not done this theory of computation course? At least the first part of it. Everybody
There
has done.
should be quite a few people because it's an optional course for MTechCS. So
Okay.
for people from maths background might not have taken it.
Okay, so in this class right now, is there anybody who has not taken it either now or previously? Dhananjay?
Can you specify what exactly you're looking for? I haven't taken a formal course, but I have studied it.
Do you know what an NFA is? So DFA is deterministic finite automata. What is NFA? Is a non-deterministic finite automata. What is it actually? Have you seen this term non-deterministic?
Yes, sir. I've seen it in context of Turing machines. Of any I'm assuming you mean non-deterministic finite state machines.
Yes.
Okay. Okay, then I understand the problem.
Okay, so what is it? Can you tell me? How can you? What does it mean? If somebody has to define you what a non-deterministic finite state machine is, how will you define it?
A machine which can only take finitely many states, but there is no clear way which decision it will make at any given state. or any given instance on the table?
Mm, I mean, there is no clear way. Okay. Mm, okay, so let me tell you what non-deterministic finite state machine is. Okay, so that means it says that there exists a path from the start state to a finishing state or accepting state. It doesn't mean that there's a unique path. There are possibly many paths, out of which one of the paths is from start state to the finishing state. Another way of putting it is this following. See, I am a dumb person. I have no clue about it. I want to check is L is in, so L say has a NFL. Okay, so that means I have been given a finite, this is an NFL. There means maybe one or multiple start states, and there are some end states. I want to check is X is in, sorry, somebody is asking something. No. So if I want to check if X is in L, how can I get it? This machine is too complicated for me to understand.
So the idea is to write down the start state, right? We first step we write down the start state, and we next step we take the first transition and the table. Then after the X is finished, if any one of the state is an accepting state, we will say that X belongs to L.
No, but that is in a different DFA.
We can get a table, right? All start states, set of all start states. Then
But
then
the
I
transition is not unique.
include all transitions.
So how will all that's too much of an argument. I mean,
So I think he is referring to the tree that we can build for all the paths possible, and if the leaves of the
that's a
Hello, am I
massive
audible?
tree. Hello,
Yes, I was thinking about that.
that's a massive tree. Think of it. You have to convince me that X is in L. How will you convince me? How will you convince me X is in L?
Give one path.
Give me one path, right?
Yeah.
So X is in L meaning you can provide a witness. Okay. Now let's think of this ILP. I have told you this ILP doesn't have a solution, right? So ILP doesn't have a solution. Okay. So this one doesn't have a solution. I'm sorry, it has a solution. It doesn't have a polynomial time algorithm. Okay, this is the ILP you're talking about. I'm not solving this optimization, but think of the decision version of this problem. Meaning, is there a maximum which achieves this one more than 100? Can I solve it? I'm told that there is no solution. There is no solution because, I mean, sorry, there is a solution, but there is no fast, efficient algorithm. There is no p-time algorithm. But I am a dumb person. You are not. How are you going to convince me that the maximum is more than 10? How will you
What is
convince?
the last question? The maximum is more than 10.
So I want to know this whole problem that given this instance, is there a setting of x1 to x6 such that it is more than 10? Say
Verification problem. Just show one solution.
you have to just give me one solution, right? So to convince me, so consider what is the decision version of the problem. It is there a solution which such that this quantity is more than some k, right? such that the constraints are satisfied. Now, I am an idiot. I don't know do anything, but you are a super smart person. You can tell me, oh, see, why don't you put x1 equals to 1, maybe x2 equals to 0, x3 equals to 1, x4 equals to 1, x5 0, x6 0, and please check it for yourself. What is the that these constraints are satisfied, and the maxi and the value of this is more than k. I am not that bad. I can check the constraints. I can check the constraints are satisfied. I can check the maximization is more than k. So see, what is it? I am a person who don't know how to, so say I don't know how to find a solution. Find a solution efficiently. But I can check if a solution is correct efficiently. Oops. So I can check whether a solution is correct and I can do that efficiently, but I don't know how to find the solution. Now, this is a very important piece here. Okay. This class of languages that falls under this category is what is called NP, non-deterministic polynomial time. It is not saying it is not polynomial time. I'm again repeating it. It is non-deterministic polytime. So basically, this is the set of all languages that for which, so this is the set of problems whose solution can be verified in polytime. This is something that is example is given is something like Akbar and Birbal. Like Birbal was a super smart guy. He could come up with any solution. But Birbal could not find out solutions. That's fine. But Akbar could not be fooled either. So Birbal had to give Akbar a proof, and Akbar could verify whether Birbal's solutions are correct or wrong. Or similar thing is teacher and student. So I can ask you a question in your end sample. Maybe I don't know the solution of it, and I don't need to know the solution of it. You guys are supposed to solve it. All I need to do is that I have to be smart enough to verify whether your solution is correct or not. So that is NP. So if you want me to write down the definition of NP formally, I can do that. What is it? So again, same thing. When is in L is in NP? A language L is in NP if, now this is a bit complicated, okay? Of course, I have to first, if there exists an algorithm A, okay, and a polynomial P, so polynomial P, and the polynomial P such that, okay, now for all x, now this is important, for all x in L, not for all x, for all x in L, there exists an y. Okay, how big an y is? Size of y is less than say p times x. So this x, y can be a little bit bigger. So this is called the witness. Okay, this is the witness. Okay. That a of x comma y, x, y, comma L, right? I have given this problem. This is 1. Now that means it's a witness. Now this is very careful. Now what happens if it is not in L? And for every x that is not in L, okay, so there is no solution. There's a problem that has no solution.
Sir, sir,
Yeah.
what do you mean by the size of y is polynomial of x?
So the solution size is not an exponential time. So for example, you have, in the case of this path, right? You cannot give me an infinite path.
Yes,
You have to
yes,
give me
okay.
a path that is polynomial in size of x. I mean, in this case, it is obvious it has to be polynomial in size of x. Okay.
Yeah,
But-
it's finite.
But it's, yeah, but there are problems in which it is not at all clear that the solution has to have a polytime algorithm, polytime length path.
But there should be also some constraint on this algorithm A that we are defining, right?
So this A is, of course, I'll come to that. Just one second.
Okay.
But more importantly, okay, if x is not in L, then for any y in sigma star, we have no clue what is it. Okay, Birbal can try to cheat, can come up with various solutions. This algorithm will reject. Okay, and of course, as you guys told, and A has runtime poly in x. I mean p of x. So that means A is a polynomial time algorithm. If x is in the solution, there exists a witness, not all witness, but some witness can be given such that the algorithm is going to accept it. Okay, good. You have convinced me that the x is in A. But if x is not in A, then irrespective of whatever way it tries, it is not going to convince it. Now, this is what is the call of NP. It's a bit skewed. Why? Just if I find a y and I find that, oh, AXY is in L, AXY is 0, do I mean that x is not in L? If I manage to find a y,
No.
and I find that AXY is 0, it doesn't mean that the x is not in L. It just says that we have not yet got a solution or for AXY is in L, so that x is in L. If I get it to be 1, then I can say yes, x is in L. But if I get to 0, I cannot say x is in L. So this is bit skewed. This is the bit skewed thing. Okay, so this is the definition of NP. Okay.
So sir,
Now,
it readily follows that P is a subset of NP.
P is a subset of NP. It readily follows. Think about it.
Just
Okay.
use the same A, which is the same.
But something weird happens now. Oh, yeah. Yes.
Sir,
So-
just one question. Why did we
Yeah.
require the constraint on the size of y?
So let me give you an example.
If the algorithm in itself runs on poly of size of
So
x,
think of this way. Okay. Here. Okay. This is an example. Okay. And no, actually, there exists an x. I mean, a way of putting. I mean, if it is not, if it is a forget between 0 and 1. So I say that x1 to xn, are integers, just integers, plain. They're bigger, they're integers bigger than 0. Then you cannot come up and say that, see, there exists a way of putting it when the integers are massive, not even polynomial compared to the input size. That's not good enough for us.
So then shouldn't you write the second polynomial as a function of both x and y?
You can write it, but
Then you
Exactly.
since
The second, if
that
we
doesn't
have
matter
that
that much.
if we have that the algorithm has a runtime of polynomial on size of x, then it is in some sense implied
Yeah,
that
you're
y is
right. I
not
mean,
pro-
I just
real
told
polynomial.
this way that, I mean, yeah, maybe if you want to write it in this way, I can write it. So maybe that's what the confusion is. So
Yes, I was
So-
saying that
plus size of x. But again, this doesn't matter because this is a polynomial. So y is also polynomial. So this is a polynomial in size of x.
yes, that reduction is coming from the concern on size of y.
Yes, but the previous inequality isn't justified if you write it without y.
Okay, fine, good. So yeah. So maybe I should just comment one thing here. Note that there is also, I will use a different color here, okay, to kind of ensure that there is another notion called co-NP. Exactly the opposite of this. In which case, like here, you are talking about what happens if x is in L, then you output 1, if there exists one, right? And so in co-NP, instead of this for all, this becomes there exists, and this becomes for all. It becomes there. Okay. That's kind of the flipping of this side, meaning the fact that there doesn't exist a solution has a proof. Okay. So go back and think a little bit on this thing. So how we draw it is that this is called the co-NP, and this is called the NP. This is the graphically we draw this object, not graphically, I mean pictorially. NP, P, and in between here in the intersection of both is this class P. This is a typical drawing of a pictorial representation of NP and co-NP. Okay. Good. Now there are a lot of things to say which I cannot say right now. I have to stop right away. First of all, go and prove that ILP is in NP. Now this is, you can prove it. You can almost verify it almost some level. And your job will be that to prove that the rest of the problem, use ILP to solve the other 3 problems or other 2 problems, whatever. Now I can say this thing very confidently that you can do that. Why? Because we have called a reduction. In some sense, we have told that problem 1 we reduced to, this is a reduction, it's called. This is how the notation has, it's a polytime reduction, it's called. It's a reduction to LP. I reduced the problem to LP, meaning LP is harder than problem 1. Since LP can be solved in polynomial time, I can use that solution to solve problem 1. Okay, this notation is called reduced to. And this P here indicate polynomial time, meaning the LP instance is just a polynomial size, in the size of the LP instance, the polynomial of the size of the problem that was given. Second problem, we reduced to what?
An ILP.
An ILP. Okay. I want you to do the same thing for the other 2 problems. And the next class, we will prove this nice theorem, or not prove it. Maybe we can state it and kind of look into it. This is a theorem. Any problem in NP, any problem L in NP can be reduced to ILP. Any problem.
Sir, can you give an exact definition of reduction? Like, do you mean that every solution to problem 1 should be a solution, or every
Yes,
solution found by the LP
yes,
should
yes. So, okay, so see, L, this is a subset of sigma star. I will think of an ILP also as a sigma star, right? Then a reduction from F to, so reduction from F to P to L, right? ILP, this is basically, we call this a function from sigma star to sigma star, such that for all x is in L if and only if f of x is in ILP.
I see. So relaxation to an LP of an ILP is not a reduction.
No. That is something different.
And does this function f is required to be a bijection?
It doesn't, no, it's not a bijection, not at all.
Okay.
It has to be polytime. That's a different issue. Polynomial size. So f of x, size of f of x should be less than poly of size of x.
Okay.
Sir, could you scroll up to the diagram you drew, the set diagram?
Yeah.
Are you implying that there are problems which are both NP and co-NP but not K?
I mean, that's the standard belief. I don't have a proof for it. We know a lot of things. If you can solve this problem, you will be winning $1 million. Have you heard of this question?
Yes, sir. So are they? Oh, okay. I see.
This is the $1 million question. And more than
So there are
$1
no
million.
known problems.
If you prove this one, there it's a two-way sword. You will earn accolades from people in the industry, academia like crazy. You will be considered to be the god in the field, and you will possibly be killed because the crypto people will come behind you, because the whole of the crypto system will collapse.
Isn't the general belief the other way? He is not equal.
Yes, the general belief is other way, but if you, that's why. I mean, because if this is true, then you're nothing in the banking sector is safe. If P is equals 20, then nothing in the banking sector is safe. So, okay, I think I'll stop here today. Okay, there are a lot of things to be done in the next class and all. As you can see, we have to go a bit slow over here. They're a bit abstract. So I am going to request you guys to please go for it as much as you can. No books and all report, just follow my notes. That should be good enough. Okay. If you want to look at books and all, it's perfectly fine. Okay, so, and without this understanding, this is the most beautiful part of the algorithm possible. Well, lots of these nice things comes up. Okay, this theorem is something that is a hard theorem. We will prove it. And this is a massively big theorem. We'll prove, prove it, or I don't know what we'll do. Let's see. But we'll, at least we'll give you pointers to it and all. Okay.
Hello, sir. Before we end,
Yeah.
two things regarding the assignments. First is that can you just provide any sample solution to any of the problems in the problem set, preferably the matrix multiplication one, so we can get a clear idea about how to formulate the solutions for this kind of problems?
I suggest that why don't you write a mail to your TS and they will be giving you.
Okay, and additionally, either from in the tutorial or in class, don't think it's possible in class anymore. a discussion on traveling salesman problems and related problems.
Traveling salesman problem. Okay, why traveling salesman problem
So,
particularly?
as per like the way I have solved up till now the assignment, I think two of the problems are closely related to traveling salesman problem. And like I've gone through that from the reading materials, but I think
Really,
class.
traveling salesman problem. Okay, I mean, we will come to traveling salesman problem possibly sometime in some time, but traveling salesman problem should not be coming.
Okay, then I will be mailing you regarding.
Sure.
So I think the garage sales problem is something somewhat like traveling salesman problem.
Yeah. So
Oh, wait,
Yes,
isn't
it
it
would
just an
be
answer?
yeah, I
very
will
similar
discuss on this
solution,
one.
I
Traveling salesman problem will come certainly. We will be talking about it a little bit, at least certainly in the next few classes. Okay. Yeah. Okay, ठीक है. I think that means stop now. Okay. Yeah, Akshay, you have something to ask?
His hand was raised.
Oh,
Yes, sir.
okay, okay. Yeah.
Was for it.
Okay, so thanks. See,